In this video, we'll go over L'Hopital's rule. This rule states that the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. Now, the only time you're allowed to use L'Hopital's rule is if you have an indeterminate form. So what that means is if you plug in a to f of x over g of x into the limit and you end up with something like 0 over 0 or infinity over infinity or infinity minus infinity or 0 to the 0, 1 to the infinity, and infinity to 0, these are all called indeterminate forms. Indeterminate forms. So once again, if you plug in a into your function, your f of x over g of x, and you get any of these values, you're going to want to use L'Hopital's rule, which is the limit as x approaches a of f prime of x over g prime of x. And it's pronounced L'Hopital's rule. If you want to piss people off, you can say L'Hospital's rule or something like that. But this is L'Hopital's rule. For our first example, let's take a limit of secant x minus tangent x as x approaches pi over 2. So the first thing that rings off alarms to me is secant and tangent. So let's rewrite that in terms of sine and cosine. So secant is 1 over cosine x. Tangent is sine over sine, or sine x over cosine x. And because we have a common denominator of cosine x, we can combine these into one expression. So we'll have 1 minus sine x in the numerator divided by cosine x in the denominator. Now let's take the limit of this. So we have the limit as x approaches pi over 2 of 1 minus sine x cosine x. So let's plug in pi over 2. So if we plug in pi over 2, we get the limit as x approaches pi over 2 of 1 minus sine of pi over 2 is 1, and cosine of pi over 2 is 0. So we get 0 over 0. Now, if you remember from the beginning, this is an indeterminate form. So now, instead of leaving this as the answer, which is completely incorrect, let's use L'Hopital's rule. I'm going to erase this. Whenever you use L'Hopital's rule, draw a line or an arrow or signify somehow that you use L'Hopital's rule. So I'm going to abbreviate L'(H) and draw in a little arrow here. So the person who sees my work or grades it knows that I've used L'Hopital's rule. So L'Hopital's rule states that the limit of f of x over g of x as x approaches a is equal to the limit of f prime of x over g prime of x as x approaches a. So we're going to have the limit of x as x approaches a, in this case is pi over 2. And we'll call f of x 1 minus sine x. So the derivative of 1 minus sine x, the derivative of any constant is 0. The derivative of sine x is just cosine x. So we get 0 minus cosine x in the numerator. And then the derivative of cosine x is negative sine x. So now that we have that, we can cancel out the negatives. I'm going to rewrite the limit below here. So the negatives cancel out. We're left with cosine x over sine x. Now let's plug in pi over 2 and see what we get. So cosine of pi over 2 is 0. And then sine of pi over 2 is 1. And 0 over 1 is 0. So our final answer to the limit of secant x minus tangent x as x approaches pi over 2 is going to be 0. For our second problem, let's evaluate the limit of 1 plus sine 2x all to the 1 over x power as x approaches 0 from the right. So this problem is a lot trickier than the last problem, and these types of problems are probably some of the most difficult applications of L'Hopital's rule that are out there. So our first step is we gotta rewrite this into a prettier form, because this right now it's atrocious. Nobody wants to deal with this. So if you remember, if we want to take the derivative of something like y equals x to the x, we'd have to take the natural log of y equals the natural log of x to the x, which can be written as natural log of y equals x to the ln x, because our logarithmic rules allow us to bring the power over in the front, so we end up with something like this. So the concept is pretty much similar with this. We're going to bring the 1x in front, but in order to do that, we have to take the natural log. So I'm going to call this y. And I'm going to say the limit as x approaches 0 from the right of the natural log of y equals 1 over x times the natural log of 1 plus sine 2x. See what we did there? We called this part y, and then we took the natural log of that. It's equivalent to the natural log of this, and then if we take the natural log of that, it allows us to bring the exponent 1 over x into the front. So that's exactly what we did here. So now let's evaluate this. So let's take the limit as x approaches 0 from the right of 1 over x times ln 1 plus sine 2x, or which can also be rewritten as ln of 1 plus sine 2x all over x. Move the limit here. So let's plug in 0 and see what we get. So sine of 2 times 0 is 0. So sine of 0 is I think it's just 0. So we're gonna have ln of 1 over 0, and ln of 1 is 0, so we'll have 0 over 0. Because we have an indeterminate form now, we're allowed to use L'Hopital's rule. So we couldn't use L'Hopital's rule from here because, well, this isn't an indeterminate form if you plug in 0. Or, I mean, it is, but it's a messy form. So we wanted to get to something like this. We can work with this. So we'll call the numerator f of x, and we'll call the denominator g of x. And now let's take the derivative. Again, I'm going to write my little arrows to signify that I'm using L'Hopital's rule. And I'm going to have the limit as x approaches 0 from the right of f prime. So let's take the derivative of ln of 1 plus sine 2x. So that's going to give us the derivative of natural log x equals x prime over x, basically. So we're gonna start with, we'll find x prime. So in that case, that's just the derivative of this. This is just chain rule application. So the derivative of 1 plus 2, the derivative of 1 plus sine 2x is going to be cosine 2x. Now I have to take derivative of the 2 inside, which gives us 2. So I'm going to put the 2 out here. And then it's all over just normal x. That would be 1 plus sine 2x. And then in the denominator, the derivative of x is just 1. So if you don't know how I got here from this, you should watch a video on the chain rule or logarithmic differentiation. Now from here, we can just rewrite this as the limit as x approaches 0 from the right of 2 cosine 2x over 1 plus sine 2x. And we can plug in 0 now for x, so that'll give us 2 times cosine of 0. Cosine is 1, so we're left with 2 over, and then sine of 0, 2 times 0 is 0. So sine of 0 is 0, so we're left with just 1 plus 0, which is just 1, so it gives us 2. But 2 is not our final answer. Again, we had to rewrite the expression up here to make the natural log of y equal 2. So this is true for 2 is a limit as x approaches 0 of this function, but again, it's not the same as this because there's a natural log right here. So let's rewrite this like we did before. So we know the limit as x approaches 0 from the right of natural log of y equals this. Now we just solved the limit of this. We got 2. So we're going to put 0 here. We're going to put 2. Again, this is equal to this, and we just found the limit of this, and it's 2. So the limit as x approaches 0 from the right of the natural log of y equals 2. Now, if you want to just get y by itself, because again, we called this portion of the function y, and we're only trying to find a limit for this portion. What do you have to do? Well, we can e both sides, and we'll get the limit as x approaches 0 from the right of e to the ln y equals e to the 2, or e squared. This cancels out, so we're left with the limit as x approaches 0 from the right of y equals e squared. And again, y is what we have here earlier. We have y. So I can now say the limit as x approaches 0 from the right of 1 plus sine 2x all to the 1 over x power equals e squared. So this is our final answer. Now when you do these problems and you use this lny method, do not forget this is not your final answer. You need to set lny equal to this value and then solve for y. Thanks for watching and happy Thanksgiving. Or happy early Thanksgiving.